Assalamualaikum warahmatullahi wabarakatuh. My name is Ashraf bin Salwi. So today I want to explain about lab 4, actually a synchronous motor or synchronous generator, about the procedure for the part 1. So synchronous generator. In three-phase synchronous generator, the stronger the rotor electromagnet, the greater the magnetic flux linking the stator winding, and the higher the alternating voltage induced across the stator windings. Furthermore, since the induced voltages are proportional to the rate of change of the magnetic flux linking the stator winding, one can easily deduct that the faster the rotor turns, the higher the amplitude of the induced voltage. In brief, the amplitude of the voltage produced by a three-phase synchronous generator is proportional to the strength of the rotor electromagnetic and the rotation speed. This is what we call it some characteristic of the synchronous generator that we have to know. So let's go to the procedure. So synchronous generator no load operation procedure. Firstly, we must install the equipment that required in the EMF workstation. So actually we have 4 equipment, which is synchronous motor generator, prime mover, dynamometer, power supply, and data acquisition interface. So basically in this lab we use LV sim EMF to simulate the lab. So second, on the power supply, make sure the main power switch in off position and the voltage control knob is turned fully counterclockwise. So as you can see on this circuit, this is knob, so make sure we already fully counterclockwise this, and the power is turned off first. Okay, then we go to the next step, the next procedure. So ensure the power supply is connected in 3-phase power supply. Then connect the power input of the data acquisition module to 24 volts AC output of the power supply. So as you can see, this is data acquisition interface. So this is a 24 volt that already connect to the power supply. Then we go to the next procedure. On the power supply, okay, set the 24 volt AC power switch to the on position. So to turn on, we just click here. And then the motor start running. This is for the running of the motor. It will be explained in the earlier parts. She will explain all the data that need from the lab 4. So actually we construct this circuit connection based on the connection that given to us. This is a circuit connection. So that's all from me. Thank you.
Okay, let me show you how the motor is working. Firstly, turn the power supply on. Set the prime mover speed indicated by the speed meter in the metering window so that it is equal to the nominal speed of the synchronous motor or generator. Okay, firstly you have to turn on the power supply. And then you can see here the synchronous motor and prime mover are moving. Next, in the oscilloscope window, make the appropriate settings to observe the waveforms of the voltage on channels E1, E2 and E3. That is, the voltage induced across of the stator windings of the synchronous generator. Okay, to see the waveform, you have to press here. And then view and continuous refresh. So this is the waveform of E1, E2 and E3 signal. Okay, let's take a look at some questions. Are the waveforms sinusoidal? Yes. And second, what is the approximate phase shift between each of the voltage waveforms? Since we get the waveform is sine, so the approximate phase shift is 180 degrees. Next, in the oscilloscope window, select the display continuous refresh function. Slowly adjust the prime mover speed until it is approximately equal to 1000 r/min. While doing this, observe the waveforms of the voltage on channels E1, E2, and E3 in the oscilloscope window. And how do the amplitude and frequency of the voltage waveforms vary when the speed of the synchronous generator is decreased? Briefly explain why. So the answer is, decreasing the synchronous generator speed will decrease the amplitude and frequency of the sine wave voltage. Number 4. Does varying the speed of the synchronous generator affect the phase shift between the voltage waveforms, and why? Phase shift is determined by the build of the motor, so it is not affected by varying speed. Number 5. On the synchronous motor generator, slowly turn the exciter knob counterclockwise to decrease the field current. While doing this, observe the waveforms of voltage on channels E1, E2, and E3 of the oscilloscope. How does the amplitude of the voltage waveforms vary when the field current of the synchronous generator is decreased? Briefly explain why. So the answer is, the amplitude of the voltage waveforms produced by the three-phase synchronous generator increases as the generator field current. IF decreases and vice versa. Since the resistor and the supply voltage remain constant, so the voltage must be increased to compensate for the decrease in current. Therefore, the amplitude of the voltage waveform increase. And the last one, does varying the field current of the synchronous generator affect the frequency of the voltage waveforms and the phase shift between the voltage waveforms, and why? So the answer is, varying field current of the synchronous generator and phase shift is a set value determined when the generator is built. Next, I will explain the characteristic of a synchronous generator. Basically, this is the circuit used to observe the no-load operation of a synchronous generator that we have modified. The frequency meter in the metering window will be used to measure the frequency of the voltage produced by the synchronous generator. Turn the power supply on and set the prime mover speed so that it is equal to the nominal speed of the synchronous motor generator. Okay, firstly we have to turn on the power supply. And as you can see here, the prime mover and synchronous motor generator are moving. In this part, they ask us to record the frequency of the voltage produced by the synchronous generator in the following blank space. This frequency is indicated in the column frequency of the data table. So the frequency that we get is 83.50 Hz. Then calculate the theoretical frequency of the voltage produced by the synchronous motor generator using the following equation. P is the number of pairs of poles per stator winding. So this is the equation. F equal to N multiplied by P divided with 60. So what we get is 83.43 Hz. And then the next question, compare the measured and calculated frequency. Are they approximately equal? The answer is yes. For the next question, briefly explain why the relationship between the synchronous generator output voltage and field current is non-linear for high values of current. So the answer is, As the field current rises, the stator voltage increases proportionally. For most machines at about 80% of rated voltage, the curve becomes nonlinear, showing the effects of magnetic saturation. If the straight line characteristic is continued, the so-called A-gap line results. In the short circuit test, the rotor is turned at rated speed with a three-phase short circuit on the stator. As before, increasing the field current allows the plotting of the stator current versus the field current. A typical short circuit characteristic, the short circuit characteristic is linear. The flux density in the machine is very low since the terminal voltage is zero. The A gap flux is sufficient to produce a voltage to overcome the leakage reactance drop. Next question. Describe how the synchronous generator output voltage varies as the speed varies. So the answer is, in synchronous generator, the speed of rotation of the rotor is equal to the speed of the rotation of the field at the stator. Excitation field current, the voltage is directly proportional to the speed. The rate of change is proportional to both the magnitude of the flux and the speed of the generator. Thus, the voltage is directly proportional to the speed and the field current. The last question is, describe how the frequency of the voltage produced by the synchronous generator varies as the speed varies. So the answer is, the frequency of the generated voltage depends upon the number of field poles and on the speed at which the field poles are rotated. One complete cycle of voltage is generated in an armature coil when a pair of field poles passes over the coil. In one revolution of the rotor, an armature coil is cut by P over 2 north poles and P over 2 south poles, since one cycle is generated in an armature coil when the pair of field poles passes over the coil. The number of cycles generated in one revolution of the rotor will be equal to the number of pairs of the poles. If speed increases, number of cycles covered by rotor per second increases, and hence increases frequency.
Assalamualaikum and hi. So now I will explain about review question net 4. So review questions, there are 5 questions that need to be answered. So let's go to the question one by one. So first question, they ask most electrical power that is constantly produced by. So we go to the answer one by one. So A, synchronous condenser. Synchronous condenser is a DC excited synchronous motor whose shaft is not connected to anything but spin freely. So the purpose for synchronous condenser is not convert electrical power to mechanical power or vice versa, but to adjust condition for electrical transmission grid. So it's not consume too much electrical power. So let's go to B, synchronous generator. Synchronous generator nowadays consume too much power, too much electrical power. Because industry nowadays use synchronous generator. Many other machine that use synchronous generators. More it's consume most electrical power. So let's go to other C, alternators. Alternator is also called by synchronous generators. So it's just the same as B. So the answer is D, both D and C. So that's answer for number 1. So let's go to the number 2. So number 2, when the speed of synchronous generator is increased. So when the speed of synchronous generator increase, both output and frequency also increase. So let's go through by one. A, the output voltage increase and the frequency decrease. It's not the answer. So let's go to B, the output voltage decreases and the frequency increases. So it's not also the answer. And C, both the output voltage and frequency decrease. C also not the answer, it should be increased. So lastly, D, both the output voltage and frequency increase. Yes, this is the answer that we're looking for. So the answer is D for number 2. So let's go to number 3. So number 3, how does the field current affect the frequency of the voltage produced by the three-phase synchronous generator? So as we know, synchronous generator, the field current is not, the changes of field current is not affected by the frequency of the synchronous generator. So let's go through by one. A is say frequency increase as the current increases. No, it's not answer. B, frequency decreases as field current decreases. Also not the answer because frequency and field current is not affected at all. So C, frequency is not affected by changes in field current. So the answer should be C. And D is both A and B. Of course, the answer is C because A and B is totally wrong. So let's go to number 4. Multiplying the speed of an alternator by T is divided by 60 allows the theoretical frequency to be determined, theoretical output voltage to be determined, theoretical field current to be determined, number of poles to be determined. But multiply the speed of the generator. When multiplying the speed of the generator by T60 allows the, okay, it should be the answer for number 4 is theoretical frequency to be determined. It's not the output, it's not the field current, it's not the number of poles. So the answer is A. So let's go to the final questions, which is alternator is another name for. So we already know the alternator. At the beginning, the alternator is also called by name synchronous generator. So the answer should be three-phase synchronous generator. So number 1 is synchronous motor. No, not the answer. B, yes, B is the answer, synchronous generator. But you see a C three-phase synchronous condenser. No, it's not the three-phase synchronous condenser. B, three-phase AC to DC converter. Absolutely no. So the answer is B, three-phase synchronous generator. That's all from me. I hope you understand. Thank you.
Assalamualaikum warahmatullahi wabarakatuh. My name is Adi. So the conclusion is we observe that a three-phase synchronous generator produces three sine wave voltage. They are phase shifted by 120 degrees for each other. We saw that decreasing the synchronous generator speed decrease the amplitude and frequency of the sine wave voltage. So we also observe that decreasing the field current of the synchronous generator decreased the amplitude of the sine wave voltage. We plot a graph of the synchronous generator output voltage versus the field current. We plot a graph of the synchronous generator output voltage and frequency versus speed. So this graph shows that the output voltage and frequency are proportional to the synchronous generator speed.